century Luke Morgan, who's giving our colloquium today, who's going to tell us about graphs with lots of symmetries.
Thank you, Colbert, and thank you very much to the organisers for the opportunity to be here in Cambridge. It's very nice to be here. And thank you for the invitation for a talk. So today I'm going to talk about graphs. So always for me, gamma will denote a graph. So throughout the talk, whenever you see gamma, some finite graph, it's going to be simple, and I want it to be connected. These are fairly innocent assumptions, and I always want to have some group G, which is going to be a subgroup of the automorphism group. So most graphs have trivial automorphism group, and that would mean that G was trivial. I don't want to think about that case. So I want to have some symmetry, so I'm going to make some assumption on the type of symmetry that I have. And the symmetry that I want comes from what I'm calling local properties. So it's local in the graph sense means around a vertex. So the condition that I want to hold is that for all x in my vertex set of graph, I want that the group G sub x, this is the stabilizer in G of the vertex x, is transitive on gamma of x, which is the set of neighbours of x. So these are the vertices in gamma such that xy is an edge of gamma. Okay, so this is a nice property. It means that around every vertex, your vertex stabilizer is transitive on the set of vertices adjacent to it. So it's a very simple, very subtle, very innocent assumption. If this holds, we say that gamma is locally transitive. So here local is, again, this condition around a given vertex. So it follows from some of these conditions that actually the group G acts transitively on the edges of a graph. So because it's connected, if you want to think about some path like this in your graph, maybe the path looks like this, and I'll claim that I can map this edge to this edge over here, you can kind of think about how to do this. You start with the stabilizer of y, you map x to some vertex here, then you take that maps this edge there, and then you rotate at that one, and you rotate, and you rotate, and you rotate, and you zigzag around the graph. So just using this assumption of gx being transitive, this condition about the graph being connected, I say that I'm actually transitive on the edges. So I'm talking about edge transitive graphs. And of course, if you're edge transitive, then you have at most two orbits on the vertices. It could be that you actually just have one orbit on the vertices. So we have at most two orbits on the vertex set, possibly just one. So possibly got a vertex transitive. Being vertex transitive sounds like a global assumption. It's an assumption that it's happening at on the whole vertex set. So it feels like it's a global assumption. But it's not really, because when you combine this condition with the condition that, for example, say GE for E some edge of my graph is transitive on E, which is a pair of vertices, say x, y. And if you have this condition plus this edge transitivity, you can basically, you're transitive on the two vertices which form an edge, then you can rapidly get vertex transitivity. Just use this condition again. I want to map x to actually z. At some point I've mapped this edge here, and then I just flip it using my edge stabilizer. So it is still a local assumption. So these are our hypotheses. These are the kind of graphs that I like to study. I want to give you two examples. So there's two very standard examples. So the first is the famous, which apparently has to appear in every single talk on graph theory, the Peterson graph. So here's that, looking very unsymmetrical. So good point to say we don't care about our drawings, we're just dealing with abstract graphs, so the symmetry was quite messy. And examples should be illustrative, right? So using this example, you should immediately say, oh yes, this is a graph on which this property over here holds. If I stabilise this vertex, I can be transitive on the three neighbours around it, because, well, that's clear from the picture, right? Not really, but you do know what this group is if you remember seeing it in your early course on graph theory, say. The vertices here are the two subsets of the point of the set 1 up to 5. So say maybe this vertex is the subset 1, 2. And then you join it to every other subset that it has a trivial intersection with. So for example, this is joined to 3, 4, to 4, 5, and the remaining vertex in the middle would be 3, 5. Okay, so that's the Peterson graph. We've all seen that, probably. The automorphism group of the Peterson graph then is actually isomorphic to S5. I'm not claiming that's obvious to see from the beginning either. Okay, so this is a nice example. You can, now that I've told you what this vertex is, you can probably calculate what the stabiliser is, and you can check this claim I had that the stabiliser of this vertex is transitive on the three neighbours of it. So the stabiliser of this thing should be the group generated by the transition 1, 2, and then the whole S3 on the remaining points, and then you can clearly see you can map those two things already. So it's actually, it is easy to see. So that's an easy example. Here's a not so easy example. So I said graphs should be nice, they should be easy to draw, they should be symmetrical, all these things. So this graph is slightly, I hope it's better drawn than the previous one. I tried very hard to be able to do this from memory. Let's see. Okay, we have a few more entries. Voila.
Just out 3 edges.
Let's see
Give me some edges to the right hand side.
on the right hand side top.
Oh, thank you. So, then you know what this graph is? This is the Coxeter graph. So C, the Coxeter graph. So this graph is named after HSM Coxeter. It's a nice graph with lots of interesting properties. There's a funny story. Apparently, Coxeter phoned, built up, and said, oh, I've just discovered this wonderful graph on 28 vertices and has all these nice properties. Have you heard of it? And Ter replied to him, yes, that's your graph. This graph had been studied by graph theorists, and they just started calling it the Coxeter graph. So then Coxeter then wrote a nice article about it, which is called My Graph. This is a, well, okay, so it's kind of easy for me to remember how to draw this picture. You can kind of see there was some algorithm I was following, and then forgot the ending section creators. It's not usually the way that you'd see it drawn, but just notice that this graph is around each vertex I have 3 neighbours. Again, it's obvious for you to see that if I fix this vertex, I can be transitive on the 3 neighbours, right? Quite clearly. If I told you where this graph came from, you could go away and check it, but it's a bit more laborious. So the vertices of these graphs are point line pairs coming from the finite plane, where this point is not on that line. And then you join 2 of them if together you take the 2 points that are here and the 2 lines. That should give you a set of 7 points. So they actually, it's a definition of a point which is not on the line, and then you take a pair of them such that they give you the whole finite plane. And that creates this dramatic graph. So the automorphism group of this thing, because it's related to the finite plane, is PGL 32. And I said over here, if I let this thing be G, then this, if I call this vertex X, we said the vertex-stabiliser was isomorphic to C2 cross X3. If you want to fix an edge, let's call this edge B, this is isomorphic to a D8. And if you chase through inside PGL32, well, the graph has 28 vertices, it's actually vertex-transitive, so you can calculate what the vertex-stabiliser is. Let's call this H. Let's call this vertex here maybe x prime. And hx prime is also isomorphic to C2 cross S3. And if we pick this edge to be here E prime, then HE prime is isomorphic to GA. And if you calculate the intersections of these two things to get GX instead GE, you get C2 cross C2, and here you get HX instead HG, is isomorphic to C2 cross C2. So
What's to stop you swapping points and lines to get the automorphism group PGR3?
Am I doing? Sorry. Thank you. If I say PGL27, are you happy?
Yes.
Yeah, thank you. Very good. I always forget which one's at the top. It's obvious, yeah, same group. Thank you very much. Good. So then with the correct group for H here, then these two things hold. So these, despite the fact that they're sort of very different graphs, this structural data that I've just pulled out is exactly the same. So this structural data I refer to as the amalgam. And amalgam, actual rigorous definition, I don't want to go to, so let me just be vague and say that the amalgams, say GX, GE, GX instead GE, and this triple, HX prime, HE prime, and HE prime instead HX prime, are the same. It turns out that that's actually the point. Despite the fact that these two graphs are completely different and have totally different automorphism groups, this local data is the same. And our local approach to working with graphs says that this is all you need to actually think about. So an amalgam is sometimes described as just this triple, perhaps with some specified embedding of this inside here. Sometimes it's described as a set with some kind of partial multiplication, where you have multiplication inside this group and its subgroup, inside this group and its subgroup, but you don't know how to multiply elements which come from these two respective things. And sometimes they're described as an amalgamated product. So the amalgamated product would be of these two groups, written as GX instead GE with GE.
You can't
straight out. I think you just meant to use the string.
Sorry.
I'm sorry.
Oh, that's great.
Thank you.
Thanks.
Okay.
Sorry, I didn't mean to intend you like
So, so this group is the free product of these two smaller groups, where you've amalgamated the subgroup that you can identify in both of them. So this is an infinite group, as long as this thing is a proper subgroup of these. And this group is the amalgamated product of GX and GE over this thing. And so you get, if you take the amalgams that you get from this thing and this thing, you actually get the same infinite group. And then how do you see these two graphs coming out? You see that there's a quotient of that infinite group to either S5 or to PGL27 over there, which gives you these two graphs. So the way of working with amalgams and graphs and the quotients like this, that's described, I guess, in detail in Say's book on trees. And it can be exploited to find all of the possible graphs that you might be interested in with this symmetry condition that I started with. So, for example, we have a theorem due to Djokovic and Miller from 1980, which says that there are exactly 7 amalgams, meaning 7 possible groups that can be written as a free product like this, which arise from 3-valent vertex-transitive let's say G, locally transitive graphs. So although there are maybe, so ignoring the first part of the sentence, we're looking at 3-valent vertex-transitive graphs which are locally transitive, meaning they have this property here, and then additionally they're vertex-transitive. I see the issue. You want to push it, right? Right. Although there are infinitely many of these graphs with these symmetry properties, there's really only 7 amalgams that you have to worry about, meaning that the 7 of these infinite groups and all of their quotients give you the finite graphs that I actually want to think about. So you don't actually have to worry about surveying this huge infinite list of cubic vertex-transitive, locally transitive graphs. You just have to think about the 7 amalgams. This is in a paper of Djokovic and Miller, this result saying that there are exactly 7, but they're using some work of Tutt's earlier. So Tutt's name should be mentioned in connection with 3-valent vertex-transitive graphs. So his work was done earlier, I think actually as early as 58. And what he showed is that if you have this amalgam here coming from a finite graph, that the order of this vertex-stabiliser here has order dividing 48. And then what they did is they went around and went through all groups that they could possibly work out and you pushed them together. So once you know that its order is at most 48, to work out exactly what the amalgam has to be, how these groups are and how they fit together, that's maybe not too difficult. But Tutt's result, which is very early, this is 58, and apparently, you would say entirely elementary, that was quite surprising. So this is with the vertex-transitive assumption here. And if we drop the vertex-transitive assumption, we have a result in the same year from Goldschmidt, which says that there are exactly 15 amalgams which come three-valent, drop the vertex-transitive bar, locally transitive graphs. And I mean, I dropped the word gamma from this, but I do mean finite graphs, because otherwise something would go completely crazy. So this happened in 1980, which is around when all the classification stuff was happening. And it's really, what he did when he was classifying this, he used what we now call the amalgam method. And really kicked off this theory of studying groups in terms of maybe a pair of subgroups which generate the group. Maybe I didn't say that up here, but it's kind of clear that here G is actually, once you've got that D8 and the C2 cross through S3, G is actually generated by this pair of subgroups. So it's studying a group just from a perspective of just 2 subgroups that you're interested in. So, for example, the amalgam method now has a chapter inside the GLS series on the classification. And after Goldschmidt published this result, then Stellmacher and Delgado extended it from the 3-valent case to high valencies, but rather than make an assumption of valency, they make a kind of local assumption about what a condition on this vertex stabilizer. But theirs is actually much bigger than this is. So that kind of birthed the amalgam method, and its use then went into the simple groups, which connects with the theory of this, the focus of this workshop. So this was an example where people were studying graphs and they started producing some group theory, and that group theory got lifted into the world of simple groups. So they were building theory which got used. So this led into tools for the CFSG. That's tools for the CFSG. Okay. Now let me switch this. So the next question you would ask, I should also mention in connection with this, so I mentioned there was the work of Stellmacher and Delgado on graphs of higher valency, but with some more restricted condition on the vertex stabilizer. And in my PhD, I looked at not the case of 3-valent graphs, which are locally transitive, but 5-valent graphs. So kind of the next interesting case, because 4-valent doesn't do much for you. And there, this number 15 jumped up to 105. So the amalgams are kind of exploding as you go. There's no reason to think that you should sit down and write down precisely every single one as the valency increases. you need some kind of stratification of them as you're going.
Is there always a finite number?
Is there always a finite number? It depends on the valency. It depends on more than the valency. So, yeah, there will be conditions, and I can tell you precisely what they are when there'll be a finite number, or at least when we believe there should be a finite number. And I'm going to touch on that in the second half of the talk. So hopefully I will answer your question during the talk. And if not, please ask at the end again. So, moving on from this, where you started out looking at the local picture and you're trying to classify amalgams, you want to then go back further into this into the graph itself, and you want to ask the question of, I said I make some kind of gentle assumption on symmetry of the graph in question. I want to know how symmetrical gamma is. And you think, well, how are you going to actually measure symmetry in this sense? It should be like, well, how big is the automorphism group? Is the automorphism group as big as it could possibly be? But that doesn't really make sense when dealing with a graph, because how big could it possibly be? Well, that's the automorphism group, it's just that. So instead you measure symmetry in a different way. Again, I'm doing it from a local perspective. So we say that gamma is, with respect to this group of automorphisms, just so we don't leave it behind, GS transitive if for all vertices in the graph, the stabiliser is transitive on the paths of length s, beginning at x.
Is that sometimes called S-arc transitive?
Yes, but could be if I put the word locally in here. So there are a couple of competing notations for this. I want to say it's locally GS transitive, and that means that I'm only making this condition on what happens at GX. If I kind of delete the locally, then I should be thinking about something global as well, so that kind of kicks into vertex-transitive. So these graphs might also be vertex-transitive. And usually when people talk about S-up transitive graphs, they mean only the vertex-transitive ones. So this assumption down here means that my graph is at least g comma 1, locally g comma 1 transitive, because I'm transitive on the vertices around it. Those are the edges adjacent to it are the paths of length 1 around it. So that's pretty innocent. And the question you might then say how to measure how big the symmetry is, how much symmetry you have, is how large could this integer s be for your given graph? Yeah. Some fingers here in a second. So, how big can S be? And the answer is, well, as big as you want, because you can always take, for example, take a cycle. And in a cycle, an SR will just be a path of length S around some vertex, so just start this vertex and go around as many times as you want. And am I transitive using the vertex-stabiliser on these paths? Yes, because there's just one that goes around as far as it wants in that direction, or another one which goes around as far as it wants in the other direction. I can just flip in my cycle. So I'm transitive on those two S paths. So S can be as big as you want, witnessed by a cycle, but it turns out that if you want to ignore this case, the case of the cycle, then it's much more restricted. So Richard Weiss proved in 1980 that, let me just check, that if gamma is locally transitive, we said I was going to call this locally G comma S transitive, and G is additionally vertex transitive, and we're not in this case, so we're not looking at a cycle, and the valency of gamma is at least 3. So the valency of the graph is the number of edges adjacent to each vertex. since I'm vertex transitive, I can talk about the valency of the graph, because every vertex has the same number of neighbours, then S is at most 7. So it turns out that if you want to measure symmetry in this local way, you're not actually going to get that much of it. But S is already quite a large, 7 is already quite a large number, and there are examples which witness this, which come from generalized something, generalized axioms. So this is witnessed, S equals 7 is witnessed in hexagons which come from the Z-type group G2 R3 to the X. Okay, so you're allowed to have some symmetry, you want to have some symmetry, but you can't have too much. This is in 1980. This is using the classification. Although 1980 sounds like a strange year to be using classification, doesn't it? Let me check that. So, what about, this is where you have vertex transitivity as well, and you might ask the question, let's just drop that, what could go wrong? It took a while for this to be answered. This was only recently published, by Stelmacher and Van Boom in 2015. So, if gamma is locally GS transitive, we don't need the vertex transitivity assumption, but now we do need to make some assumption about the valency, and some vertex has valency at least 3. Then S is at most 14. So this was in 2015 and this was in 1980. So it took a while for this to come through. So there was apparently some work done on this already, maybe as early as 1996, but it took until 2015 for the full proof to come through. There's a nice, so in this paper from 2015, there's a nice quote which I would like to read for you. It says that about the strategy of the proof. The strategy of the proof is similar to that of the classification of finite simple groups, but of course on a much more elementary level. So, if you think about reading this paper, which is something like 60 pages, with the idea that this is going to give you some nice indication of how the classification goes, I think that makes it kind of a nice exercise. It's only 60 pages. You can squish this S at most 14. So I said some vertex has valency at least 3. Since I have this assumption, I'm edge transitive, so all my vertices have only a pair of valencies anyway. So I'm saying that like maybe one class of them has at least 3, and then the other class could just have valency 2. So if you squash those, if you ignore them, and you say every vertex has valency at least 3, this number here, S at most 14, drops to S at most 9. So, S at most 9 if all vertices have valency at least 3. But you can see where that S at most 14 comes from. If you have one vertex of valency 2, well, not one vertex, sorry, one of your vertex classes have valency 2, and the other one has valency 3. A vertex of valency 2 in your graph looks like this. So if you just ignore that one, pretend it's not there, you're looking then at a vertex-transitive graph, where every vertex has valency at least 3, so you can use Weiss's result. But now your paths, which were S paths in here, become 2S paths in the compressed graph, so you need 2 times 7 to get 14. So they really had to only think about the graph in this case. They had to prove S to the most 9 in the case where all vertices have valency at least 3. And again, this, yes?
Do graphs have, are there examples of graphs where the S goes between 9 and 14?
I don't know.
Ah, okay. I would guess 14 by the reason you just showed me. But maybe 10 or 11, 12, 13?
13 looks hard.
Aha, okay.
I think that if it is this case, it is coming from that,
Yeah.
and so you're forcing it to just be like a subdivision of the
Yeah,
vertex
yeah,
from here. So I think you would be able to achieve it, but in kind of a tricky in a kind of not image as that graph. And also I said there that the S for S equals 7 is witnessed by generalized hexagons, which come from G23. Here, this S equals 9 is witnessed again by a generalized octagon, which comes from twisted G2 over some field of power 3. So, and I wanted to say one more thing. So here, when we're dealing with this, how big S can be, and here I'm saying it's at most 9. So when you're getting these high values of S, in particular when S is at least 6, how they prove this is that they say when S is at least 6, the graph I'm looking at is actually somehow coming from the graphs that were studied earlier by Schumacher and Delgado. So they managed to get into that result, and they proved that the group has what they were calling back then a weak BM pair, and therefore this graph that they're looking at, the amalgam of vertex stabilizers within it is recognized by one which comes from generalized octagons. So there is some kind of really heavy machinery that they're using to do this. They actually, so they used the work of Schumacher and Delgado, and which itself was using the work on groups with BM pairs. So there's kind of lots of deep stuff going into that when S is at least 6. But even more recently than that, they've come back to the question on what's going on with the amalgams for large values of S. So I said that for S at least 6, the amalgams, they are already known. They were able to show that they had to be the same as the amalgams coming from the earlier work of Schumacher and Delgado. And then only just last year, very recently, they extended this analysis, and I'm going to say that if S is at least 4, the amalgam is known. And just as the comment that when S is at least 6, the bulk of their proof was to show that the amalgams were found by Delgado and Schumacher. So, if S is at least 4, we're in extremely good shape from the local point of view. We know everything about the situation we would want to. We know the whole amalgam. So, that's probably all of the data that you would want to know. So, I said this was local properties. Another question that I've been interested in for some time is the following. It's on order of vertex stabilizers. So this comes back to this question of Dave from before. Do we know if there would be finitely many amalgams? So just to make this question make sense, I have to give you a definition. So inside my vertex stabilizer, I'm going to define a normal subgroup. It's denoted like this, say GX with a superscript I. And these are the elements of my vertex stabilizer such that they, let's use it, such that they fix Z, all vertices Z which are a distance from X in the metric on the graph at most I. So it's an exercise to prove that each of these things, each I, is a normal subgroup of the vertex stabilizer. I should at least be some integer. So each of these is a normal subgroup of the vertex stabilizer, And so if you're analysing the structure of the vertex-stabiliser, this is a good series to use. If you're usually analysing the structure of a group, you want to use like a chief series or something like that. If you're working with a graph already, then you're going to have this nice series which is given to you like this. So here's Gx, there's one normal subgroup, Gx1, the second one. And then at some point down here we maybe have the identity. So this is a chain of normal subgroups inside my vertex-stabiliser. And there's kind of conjecture concerning the order. Is that the order is somehow controlled by, again, local property, and local property is to do with the permutation group. So there's a conjecture from 1708 of Richard Weiss. He said that there should exist some k, natural number, such that for all graphs gamma, which are G locally transitive, and he put on the assumption of vertex-transitivity, and such that this group, so I have the vertex-stabiliser of x for some vertex in the graph. I look at, this is the action which is induced by, so if this is x, this is its neighbourhood, gamma of x, then the group gx gamma of x is the permutation group that you get induced on this set here by the vertex-stabiliser gx. And we put on the assumption that this permutation group here that you get induced is primitive. So with these conditions, there exists some integer k such that for all graphs gamma which are locally transitive, vertex-transitive, and the local action is primitive, then gx to the k equals 1. So it's some fixed integer k which works for all graphs gamma under the assumption that they're locally transitive here, vertex-transitive, and such that this local action is primitive. So it's really strong. In the paper in 78, he doesn't phrase it like this. I kind of changed it slightly to an equivalent formulation. But I like this definition where you work with actually the vertex-stabiliser. So it says, so let me just connect back to this picture that I drew down here. This gx1, this should be the set of elements of my vertex-stabiliser which fix all of the vertices at distance 1 from x. So that means that those elements are in the kernel of the action on the neighbourhood. So it means that if you're thinking about gx gamma of x as the permutation group induced here, then also this is isomorphic to gx modulo gx to the 1. So this group gx1 is exactly the kernel of the vertex-stabiliser acting on this set. So it's saying that if the top of your group here is a primitive group on the neighbours, then there exists this k, and then at some point you're finite. Trivial. So it's kind of remarkable that this should be true. If you've seen the Sims conjecture, the Sims conjecture is also of a similar form, but the Sims conjecture makes an assumption about the global properties. So it says that if you're acting primitively on the vertex set, then kind of equivalently that there should be some integer k such that a gx to the k is trivial. But that's with the global assumption of primitivity on the vertex set. And so this is very, very similar, except your assumption of primitivity, he's put it into the local action, which is much weaker. So this conjecture is still open. I mean, it was made in 78, but there's still lots of work being done since on it. Let me give you some examples of when it's true. So, so how would you attack this, for example? We're saying that gx gamma of x is primitive, so you would use your own Ascot theorem, and you would try and go through the types, your own Ascot types, and try and do some analysis like that based on the Ascot type. So one case where it's true is the following. So, let me do this again. So, yeah, I'm not on for that. So progress. Well, the first case was due to Richard Weiss himself. I'm going to give some highlights. This is by no means a comprehensive list of the progress in conjecture. I just want to give you some examples of when it's known to be true, possibly with some indication of the difficulty involved. So there was two papers of Richard Weiss and Vladimir Trofimov from 1995 and then from 2012, where they showed that gx to the 5 is trivial if under the additional assumption of 2 transitivity. So this is a bit stronger than primitive, of course, but if you're 2 transitive on the neighbours instead, then this k you can take it to be 5. And again, they had an example which witnessed this gx to the 5, which witnessed, I feel like this should be 6. Oh, sorry, excuse me, this is a 6. And they had a nice example coming from twisted E6, where they showed that there is an example with gx to the 5 being non-trivial. So it's really as good as you could possibly hope for. So this is in the case of 2 transitive. If instead you were doing an Ascot analysis, then there were some nice results due to Pablo Stiga from 2011, which showed that gx to the 2 is trivial if gx down of x is either hs, meaning a holomorph of a simple group, hc, holomorph of a compound group, or tw, meaning a twisted root group. So for these 3 cases of the Ascot theorem, which I'm using the division into 8 types. So I think that hs would be a simple diagonal group, really, where the group that you're inducing on the factors is just a trivial group with 2 factors. So it's actually a simple diagonal group in the earlier version of the Ascot theorem. It gets called a HS group in the division into 8 types, which has been used a lot by Cheryl. Maybe came from so there's 3 types that are known in complete generality. And then in 2016, Pablo Stiga showed that gx to the 5 is trivial if gx scan of x is affine. So this had been considered before, in fact, by Richard Weiss around the same time as he made the conjecture, in the case where it was an affine group where the degree was co-prime to either 2 or 3. So if it's affine, the degree is parallel prime. If that's co-prime to 2 or 3, then there was already a result of Richard Weiss. So it took a long time from around about 1978 or close to it to 2016 to do this. The reason it took so long is that in the paper, Pablo says that what he uses is, or he says the result is essentially an application of what's called the local CGT theorem, which is due to only Ebbinghaus and Stomach. So this thing, this local CGT theorem itself this is the title of the paper with the theorem of the same name inside it. I think it was in 2012 that this one appeared, and then it was used here by Pablo in 2016. So this was developed by these authors to go into the MSS program, so the revision of the classification of fine simple groups due to Mark Frankenfeld, Stomach. So this is a tool which is to go into the revision of the classification, and now in 2016 Pablo was able to use it to prove this result. So in kind of a circular way, in fact, we started out with methods from graphs, which went to develop tools for classification, and then finally in 2016 we right back where we started, where we had tools from classification going back into graph. So this is nice. This is well, I mean, it's a nice result. It's a very nice short paper anyway. I don't actually know. For both these cases, I was kind of explicit. There should be examples which meet this. In this case, I don't know any actual example which can get you to say GX4 being non-trivial. So I'm not sure if this is even tight or if it's possible. So this is so just hopefully now I can answer your question. The idea is here when you're saying it's primitive, if the local action is primitive, there should be finitely many amalgams because it's saying the vertex stabiliser is finite. Is a bound order, so because the number of vertices out at distance k is finite, then you have to be a faithful permutation group of that, so that you're bounding the order of the vertex stabiliser in this way. So therefore there should be finite many amalgams if this local action is primitive. So for example, in the case where your graph is prime valent, then it's always primitive, so all prime valent, there should be only finite many amalgams. Obviously there are so many degrees where you have more groups than are primitive, so in that case, we expect that there are infinite many amalgams. But the question is primitive even the right word to put there? So some collaborators of mine proved that you could weaken this, and Cheryl first conjectured that actually you could still have the same conjecture. Here you could replace primitive with a weaker notion of quasi-primitive, which is a condition on normal subgroups. As you say, a group is quasi-primitive if each non-trivial normal subgroup is transitive. So it's kind of automatic to prove that each primitive group satisfies that property. So you can replace this with a weaker condition. And then, so Cheryl conjectured quasi-primitive to go here in 2000. And then as recently as maybe 2016, there was 3 authors Potocznik, Spiga, and GRA conjectured, let me box this a little, conjectured semi-primitive should be the word that you put there instead. So this notion of semi-primitive is again a condition on normal subgroups. A group is going to be semi-primitive if each normal subgroup is either transitive, and that would be the same as for quasi-primitive, or it should be semi-regular. So it's a weaker condition than quasi-primitive again. And they also proved that actually semi-primitive is the best that you can put there. Is that if you have a group where the local action is not semi-primitive, then you can prove that no such K exists. So they gave examples. So in some sense, semi-primitive is the best possible thing you can have here. So as soon as you have like a valency which allows there to be a non-semi-primitive action, you'll get infinitely many amalgams. So that's when we'll have finite or not. So since then we've been working on, well, we can't work on the Weiss conjecture because it's too hard. So since then we've been working mainly on this conjecture and trying to prove results to that. But I want to advertise instead a conjecture that we think is just as good. So I started out by talking about local transitivity. And this conjecture of Richard Weiss over there has vertex-transitivity in it. And we think you should just be able to drop the vertex-transitivity. So there's a conjecture of myself, Pablo Spiga, and Gabriel GRA. So we conjectured, maybe stupidly, we were very bold, but I think it's correct, is that there exists an integer k such that it's going to be very close to this. So it's going to be for all graphs gamma, which are G locally transitive. And so I've dropped my vertex transitive assumption. What about this? I need to make some assumption about the local action. But now there's actually 2 to worry about. And if I'm now just dealing with local transitivity, I have possibly 2 edge orbits. So let's just hide the previous conjecture. So such that both, so gx gamma of x and gy gamma of y are some edge xy, then GE to the k is trivial. So what is GE to the k? This is around an edge, and you think about it exactly the same way as I did around a vertex, but now I'm measuring the distance from an edge instead. So it's the rule, if you take the, it kind of looks like a spider with lots of legs. Let's not talk about spiders in your nightmares. If you take the things which stabilise that, there is some case such that all of these have to be trivial if this pair of local actions are semi-primitive. So we conjectured this, and we also did the partial converse thing that we had over there before. We proved that as soon as one of your local actions fails to be semi-primitive, then you can have unbounded k here. We can construct a graph for you which will have gx to whatever k you want being non-trivial. So this is definitely the right word to put here. It's just not clear whether this should be true or not. It's a much harder problem than the vertex-transitive case, because now you have a lot of more stuff going on in between gx and gy. These can be totally different types. In general, make this conjecture, put it out into the wild, hope that somebody else works on it, because I don't want to do it. It's really far too hard. But I mean, but as I said, there are very nice results that have already been proven for the Weiss conjecture. Probably we've got all of the low-hanging fruit there, so it's possible there's some stuff hanging here. Okay, I think I should finish.
Any further questions, comments, or proofs?
Is it possible to show us an example with an unbounded k? Is that too?
I can give you a very, very, so I can give you an easy example. It's not, yeah, I think it does actually accidentally fall into it. Yeah. So if you take, it's a four-valent graph. It's a cycle. So this is going to be four-valent when I draw it. Looks like this. And you imagine it's a cycle which goes around. Actually, as a graph, I think it's the product of the empty graph with a K2 or something. I'm not very good at actually saying what graphs are. So it keeps going around like this. So you pick the whatever this should be, the length of the graph as big as you want, and then if you fix your k, so fix your k in advance, and then I construct this graph which has whatever this length should be. It's like the circumference, I guess, bigger than k. When you fix the ball of radius k, you're only fixing, say, anchor here. And now down here, I can still do stuff, because between these two vertices that look like that, I can just flip these two. And so I still have a transposition down here, which is still an automorphism of the graph. It fixes this vertex up here. So say this is x, maybe this should be, down here it should be, let's just say, even k plus 2, so that the automorphism which just fixes these two, say g is in gx, not trivial, and it's in gx to the k. So this is an easy example. And if you look at this vertex, look at its neighbours, it's got 4 of them. What's the local action that you're doing? On 4 points, you have to actually preserve a system in primitivity because those are over there. So it's a D8. And D8 is maybe the smallest, nicest example of a non-semi-primitive group. So yeah, that one's there. Obviously this thing is vertex-transitive, so it's not a good example for my conjecture, but yeah, it shows.
So can I ask a question? You mentioned Spiegel's result in TW type groups.
Yeah.
So does this require that the group actually has to be primitive, or does it work for fast primitive TW?
I think it needs primitive, because the, so what he's using is that the, he's using a theorem of Thompson and Wieland, which says that in point stabiliser you should have a normal P subgroup. And then I think that in primitive groups of twisted Reed type you can't have normal P subgroup in point stabiliser.
Yeah.
But in twisted Reed groups of quasi-primitive type,
You can.
you probably can, because they're awful.
Anything.
Yeah, so it definitely doesn't extend to quasi-primitive.
Just thank Luke again. I'm afraid no wine today, but there will be wine tomorrow.